The Pedia. General Studies video lectures, notes and practice question sets for engineering service examination, and other conducted examinations. In this video we had discussed a subtopic of energy and environment which is known as ozone hole, comes under climate change. Let's start with ozone hole. It is found in two different layers of the atmosphere. Ozone in the troposphere is bad because it dirties the air and helps to form smog, which is not good to breathe. Ozone in the stratosphere is good because it protects life on Earth by absorbing some of the sun's harmful ultraviolet UV rays. Decrease in the concentration of ozone in a particular region of the atmosphere, ozone hole. The best example of such an ozone hole is the atmosphere over the Antarctic, which has only about 50% of the ozone that originally occurred there. Sources: 1. Chlorofluorocarbons CFCs. CFCs molecules are made up of chlorine, fluorine and carbon. They are used as refrigerant 66%, propellants in aerosol sprays, foaming agents in plastic manufacturing 30%, fire extinguishing agents, solvents for cleaning electronic and metallic components, for freezing foods, etc. CFCs has a wide and varied application due to its properties like non-corrosiveness, non-inflammability, low toxicity and chemical stability, etc. The residence time of CFCs in the atmosphere estimated to be between 40 and 150 years. The chemical reaction: CFCs UV radiation equals freeing chlorine atoms. A free chlorine atom ozone molecule 2 equals chlorine monoxide 0,0. Chlorine monoxide atom of oxygen equals 0,2 and reformation of the free chlorine atom. Psi. The element that destroys 0,3 chlorine is being reformed at the end of cycle. A single chlorine atom destroys thousands of ozone molecules before encountering reactive nitrogen or hydrogen compounds that eventually return chlorine to its reservoirs. Nitrogen oxides. The chemical reaction nitric oxide no catalytically destroys ozone. Nitric oxide ozone equals nitrogen dioxide O2. Nitrogen dioxide monoxide equals nitric oxide oxygen. Bromine. Containing compounds called halogens and HBFCs, that is hydrobromofluorocarbons, both used in fire extinguishers, and methyl bromide, a widely used pesticide. Each bromine atom destroys 100 times of more ozone molecules than what a chlorine atom does. Sulfuric acid particles. These particles free chlorine from molecular reservoirs, and convert reactive nitrogen into inert forms, thus preventing the formation of chlorine reservoirs. Role of polar stratospheric clouds in ozone depletion. The ice particles of the cloud provided substrates for chemical reactions which freed chlorine from its reservoirs. The reaction between HC1 and C1 on O2 is very slow, but this reaction occurs at a faster rate in the presence of a suitable substrate which is provided by the stratospheric clouds at the poles. The PSCs not only activate chlorine, but they also absorb reactive nitrogen. If nitrogen oxides were present, they would combine with chlorine monoxide to form a reservoir of chlorine nitrate, ClNO2. Every spring, a hole as big as the USA develops in the ozone layer over Antarctica, in the South Pole. A smaller hole develops each year over the Arctic, at the North Pole. Why is the ozone hole predominant at the Antarctic? The Antarctic stratosphere is much colder. The low temperature enables the formation of polar stratospheric clouds PSCs, below 20 kilometers. The vortex is a ring of rapidly circulating air that confines the ozone depletion in the Antarctic region. The longevity of the Antarctic vortex is another factor, enhancing favorable conditions for the depletion of ozone. The vortex remains, in fact, throughout the polar winter, well into mid-spring, where east vortex in the Arctic disintegrates by the time the polar spring March-April arrives. The ozone measurement instruments and techniques are varied. Some of them are the Dobson spectrophotometer and the filter ozonometer called M83, and total ozone mapping spectrometer tools in the Nimbus 7 satellite. The Yamahia technique, the most common measure of total ozone abundance, is the Dobson unit named after pioneering atmospheric physical Gordon-Dobson, which is the thickness of the ozone column compressed at standard temperature and pressure STP in millicentimeters. Next we will be discussed about a new topic of climate change, which is impact of climate change.